Hello? Okay. Hi, my name is Andy Zhang, and today I'm here to talk to you about one of the most ubiquitous problems in experiments in online platforms, the problem of interference. And so this is work that was done in collaboration with colleagues at Douyin, where I was interning at the time, including Huawei, who's also in the room, and also colleagues at MIT, which is my alma mater. So I'm going to jump right in. What is the problem of interference? Let me first situate you in a very specific problem setting, a common one, where Douyin at the time was working on rolling out a feature for HD live streaming. This feature essentially allows creators to deliver their streams in HD, going from something like this to something like this. And this is a feature that's visible to creators, so it has to be rolled out on a creator level. And the way you'd evaluate this is typically by running a creator-level A/B test. However, one of the key metrics here is to measure the impact on viewer dwell time. So this is on the other side. So now let me pose you a question. Suppose that viewers watch HD videos for 30 seconds, and they watch standard definition videos for 10 seconds each. On average, in the experiment, they watch 2 videos per day. So what, in this case, is the average treatment effect? So if we think about this naively, right, the first thing you might think of is, well, there's a 20-second effect per video. There are 2 videos per user. So on average, each user is seeing an increase of 30 minus 10 times 2 equals 40 seconds of an increase in their total watch time. So this could be correct, and it might not be correct. And we don't actually have enough information at this point to say whether that's true. So we should look a little bit in greater detail at how the process of experimentation is going to work here. So from a viewer's perspective, right, the viewer arrives, you show them a video, and randomly, this video will either be from a standard definition or from a high definition streamer. They watch the video for a certain amount of time, and then they swipe to the next video. So you see the next video, this time randomly it's high definition, they watch it for 30 seconds this time, and at this point they get tired and they leave the platform. So what are we trying to measure when you run an experiment? What we really want to know is the difference between a world in which everybody got the treatment, so here everybody gets HD, and a world in which everybody got control, so here everybody gets SD. So this is the global treatment world and the global control world. And if it were true that the outcomes from each video don't affect the other videos, and that's a huge if, by the way, if that were true, then indeed, in the first world, you would watch each of these HD videos for 30 seconds. In the second world, each of them for 20 seconds. And that naive answer that we came up with, that would have been correct. So this is a world with no interference. But in reality, things are typically a lot more complicated than this. So let me give you one specific example. So suppose your viewer is named Alice. Suppose that she has a fixed budget of 30 seconds per day to watch Douyin videos. Now, she arrives, and in the global treatment world, you're going to show her a treatment video, and she'll watch it for 30 seconds. But you should keep in mind that the only reason she's able to watch this for 30 seconds is because she still has a full budget of 30 seconds at the point at which she watches that video. And having seen that video, she now runs out of her budget, gets tired, and leaves the platform. So what's happened here? Here, because you showed her this HD video to begin with, that modified her state, being her budget, and that affected her downstream outcomes. In comparison, in the global control group, she simply, her budget is depleted much more slowly, and she's able to actually watch 3 videos before eventually running out of juice and leaving the platform. So this is a case where in global treatment, she's watching for 30 seconds. In global control, she's also watching for 30 seconds, and the actual treatment effect is 0. This is a situation with extreme interference where everything that you measured with that naive approach is actually just all due to interference. And so more generally, this is the problem that we call Markovian interference. And this is a dependence that arises between experimental units. Here, different streamers are experimental units. And that dependence arises via changes to a shared temporal state. So this is Markovian interference. Okay, this is a problem that arises everywhere in online platforms. So far, we've talked about an example at TikTok or at Douyin, where you have creators, you're running creator-level experiments, and they interfere with each other by modifying viewer state. At Uber, you might think about running rider-level pricing experiments, but riders interfere with each other by modifying the state of the shared pool of drivers. Right? Everybody shares a pool of supply. An early example is from eBay, where they're running different ranking algorithms on different customers, but all customers are competing for a finite supply of items, and they interfere with each other by using up that finite supply. The list just goes on and on. You can think about running into this problem pretty much in any kind of online platform. So how do people deal with this problem today? Most common approach is you ignore it. You simply just hope that the bias of the naive estimator is not that large, and you get on with your day. But as we've seen, this can be extremely dangerous, and I would generally not recommend that. The preferred approach is to avoid interference, but designing your experiments such that you don't have to worry about interference. And there's a few approaches to this. The most common of these is clustering, where you find groups of experimental units that don't really interact with each other that much, and then you assign treatments at a group level. Right? So this allows you to avoid interference. And there's a couple other related approaches, which I won't get too much into. And these approaches are great when you can do them, but the problem is it's usually hard to come up with good groups of users. Right? So at Douyin, it's totally unclear how you would separate streamers into different groups. So what we're going to focus on is what you're going to do if you can't ignore the problem and you can't avoid it. So we're going to say we're going to fix the experimental design to be a simple A/B test, and we're going to ask, what can we learn in this world? So fixing the design, we can talk about different estimators. And when talking about estimators, you always want to look at the bias and the variance of your estimators. So naive is going to be this point on the graph. The naive estimator has massive bias. In fact, the bias, as we've seen, can be larger than the treatment effect itself, but the variance is quite low. At the other extreme, you can actually cast this as a problem of off-policy valuation, and we'll see much more clearly why that is in a second. But for now, if you use off-policy valuation techniques here, you can actually totally eliminate the bias, but at the cost of just astronomical variance. The variance of these approaches is high to the point where we've never been able to get it to work appropriately for the problems that we're looking at. So what we'd want is an estimator that sort of comes up with a better bias-variance trade-off, and that's precisely what this talk is going to be about. I'm going to introduce an estimator. It's called differences in Qs, or DQ. This estimator has bias that's provably small. It's provably second order relative to the treatment effect. It has variance that is exponentially smaller compared to off-policy valuation. And as a result, it has great practical performance on the problems that we've looked at. OK, so this is kind of the point of the talk today. So having said that, we can now start to formalize some of these ideas. So we're going to be talking about everything in the language of Markov decision processes. So for that, we need a state space denoted by S. And in the previous example, the state space is, each state is the user's attention budget at each point in time. We need an action space. So the actions are either 0 or 1 for control or treatment. We've got a reward function, which just maps a state and an action to a scalar reward. And in this case, and in the previous example, we cared about the user's dwell time. That's our reward at each time step. There are a number of policies we're going to be interested in, where a policy maps a state to a distribution over actions. And I'll talk about these different policies in much more detail in a second. But for now, you should note that each policy has an associated transition kernel, P sub pi, which tells you how likely it is to transition from one state to another if you follow that policy. And it has a total reward. So the total reward is the key quantity we care about for a given policy. And it's defined as J pi, which is the sum over all time of the expected rewards that you accumulate when executing that policy. So in this case, in the previous example, it's your total dwell time. Okay. So what does it mean to experiment in an MDP? So the first policy we care about is called the global control policy, and we denote it as pi 0. And this policy simply chooses control at every time step, no matter what. Similarly, we have a global treatment policy, which chooses treatment at each time step. And finally, the policy that we actually execute when we run the experiment is the experiment policy pi 1/2. And this chooses control with probability 1/2 or treatment with probability 1/2 at each time step. So again, when you're running the experiment, what you're actually doing is you're executing the experiment policy. So having said that, we can now pose our problem. Given trajectories of states, actions, and rewards, SA and R, and that these trajectories are drawn according to the experiment policy pi 1/2, we want to measure the average treatment effect. which is defined as J1 minus J0. So that's the total reward under global treatment minus the total reward under global control. And from here, you can kind of see immediately why this is a problem of off-policy evaluation. We're executing one policy, the experiment policy, and we're trying to evaluate the value of two policies that we don't actually get to see, global control and global treatment. So now we can start defining the estimators that we're going to look at. And for starters, I'm just going to put up the estimand, the treatment effect. And if we look at this closely, the estimand is the average reward when you take treatment actions where states are drawn from global treatment minus the average reward when you take control actions where states are drawn from the global control state distribution. Now, the naive estimator, which we talked about at the beginning, is simply the following. It's the sum over all time of the difference between rewards when you took action 1 versus action 0, and where states are drawn according to the experiment policy. And the issue with the naive estimator is that precisely that the states are drawn from the experiment policy. So when you take an expectation, you see that, in fact, you get an expected value under the experiment policy, and that's the wrong distribution compared to the average treatment effect you'd like to estimate. So this distribution mismatch is precisely the source of bias in the naive estimator. So what can we do about this? Well, here's our estimator. So this is the differences in Q's estimator, and all we've done here is a superficially very simple thing, which is that we've taken the R's in the naive estimator and we've replaced them with Q's, right? And what is the Q value? For those of you who aren't familiar, this Q1/2 of SA simply says, if I start in state S, I take action A, and I subsequently follow my policy pi1/2, my experiment policy, forevermore, what's going to be the expected sum of future rewards? So for comparison, the naive estimator says it looks at the R values, so it's saying what's my one-step reward under treatment and control, and the Q value says, and the DQ estimator says what's my long-term value, having taken action 1 versus action 0. So that's all this estimator is. So what can we say about the bias and variance of these various estimators? So I'm going to have to introduce one more quantity, which is this quantity delta, which is just a problem parameter. It measures how close the dynamics are under treatment and control. So this P1S is the distribution over next states starting from state S. P0 if you take the treatment action. P0S is the distribution of next states starting from state S if you take control. And this delta just measures the distance between those two distributions. Okay. So this is a useful parameter, first of all, because the average treatment effect is typically ordered delta. It's pretty much just linear in delta for most problems. Now, we can look at the various estimators we've talked about. For the naive estimator, the bias is actually also ordered delta. And this essentially corroborates what we've seen before, where the bias of the naive estimator is of the same order, and it can be larger than the average treatment effect itself. On the other hand, the variance of naive estimation is constant in the size of the state space. At the other extreme, for unbiased off-policy evaluation, you have that it's by definition unbiased, but the variance has to grow at least linearly in the size of the state space. And when that size is extremely large, as it typically is, really this approach just is not practical to use. So for DQ, what we see is the bias is ordered delta squared, so it's second order relative to the average treatment effect, and the variance remains constant in the size of the state space. So ultimately, we have an estimator that trades a tiny bit of bias, in fact, an acceptable amount of bias, for a massive reduction in variance relative to unbiased estimators. And so that's essentially the power of DQ estimation. So in the time I have left, I'm going to give you a bit of intuition for why DQ works, because so far it's been just sort of a mysterious symbolic manipulation, right? So the reason it works is because it is the correct first-order approximation to the average treatment effect. To see that, we can write the objective, the total reward values explicitly as functions of pi. So we have J1 of pi and J0 of pi. And the true treatment effect is simply J1 of pi 1 minus J0 of pi 0. So this is just another way to rewrite what we've already looked at. Now, what is the naive estimator? The naive estimator is simply taking this and plugging in pi 1/2 for pi 1 and pi 0. And what does that mean? So one way to look at this is that the naive estimator is taking a 0th order approximation of the ATE around the experiment policy pi1/2. And you can kind of see where we're going to go from here. The DQ estimator takes that 0th order approximation and adds a first order correction. So you can show that this is precisely what the DQ estimator works out to be. So the reason why this works, DQ is a first order correction to naive. And this is sort of the main theoretical content of the paper. This is all powered by a novel Taylor series expansion that's useful for off-policy evaluation more broadly. And from this, you immediately get a bunch of useful results. First of all, the bias analyses that we talked about all pop out immediately by bounding the remainder of this Taylor approximation. And there are various generalizations of the estimator that are possible when you look at it from this perspective. Okay, so finally, let me show you a brief look at the experimental results. So we're running a simulation of user behavior that's calibrated to Douyin user data. And the basic idea for the simulator is very simple. It's pretty much the dynamics we discussed before, where whereas the treatment increases the user dwell time myopically for a single video, the longer the user is spin around, the more likely they are to leave the platform. And so as a result, having watched a video longer decreases the amount of time you can watch videos going forward. Right, so this is the basic dynamics of the simulation. So here's what the various estimators look like. So on the x-axis, we have the number of viewers. And this goes from 0 to about 100 million, which is order of magnitude what you'd see in a day at Douyin. Y-axis is the estimated treatment effect. And the dashed line is the true treatment effect, which is about minus 0.17%. Now, if we look at the naive estimator, we can see that the variance is pretty low. By about 10,000, 100,000 users, it's already converged to some value. But that value is a totally wrong value. It's, the naive estimator is estimating a plus 1% treatment effect, which is, first of all, it's the wrong sign. And second, it's 5 times larger in magnitude than the actual treatment effect. So this is a totally useless result. Now for DQ, what we can see here is that the variance of DQ is substantially larger than naive. But by the time you get to about 100,000 or a million users, the variance has decreased to the point where the lower bias of DQ actually allows you to obtain lower error than naive. And ultimately, DQ converges to a point with nearly 0 bias. And finally, for off-policy evaluation, this is sort of the best we could do. It looks like this. So the variance of off-policy evaluation is really just, it's huge. And nothing that we did here was, we were able to actually get it to really work well for this problem. So even at 100 million users, it's not telling you anything about the sign of the treatment effect. So this is a taste of the results, and I'll defer to the paper for the tables and for the results. And I think I'm just about out of time, so let me conclude here. So what have we done? We've introduced an MDP model for interference, which hopefully elucidates a lot of the problems that arise with interference in these models. We've introduced an estimator, differences in Qs, which is low bias and low variance. And finally, I just want to mention one more thing, that actually, in this setting, DQ can be computed without knowledge of state, can be computed in linear time in the number of observations you have. And there are variance estimates that it comes with that allow you to do inference. So it's a very practically useful estimator. So thanks for your time. Here's my contact info. And there are 2 papers that this work draws on. You can find their titles here.
So thank you. A question that comes into mind is you showed us what happened if there is cannibalism between the 2 treatments, right?
Yeah.
I'm curious to know what happens if it's not clear what do I mean by cannibalism. We said that if there is a fixed budget for each user, so there could be negative interference between the treatments. What happens if there is harmony between the 2 models? Can your model can count for it?
Yeah, that's a fantastic question. So the model deals with any sort of modification to state. So the cannibalism, those tends to be the examples most salient to people's minds. But there's no fundamental difference for that between that and positive interference in our model. And so some of the examples in this Markovian interference paper deal with positive interference.
Thank you. We got one question from the audience.
I have a naive question. So is it possible to design new experiment framework, I guess right now you have the A/B split on the creator side, but if you at the same time also have that split on the user side, that get rid of the interference that you're talking about, right? Is it possible to just run experiments in that way, and then how does it compare to your method?
Yeah, that's a great question. So there's actually a lot of work on this. So there's a couple works actually out of Amazon on what they call two-sided randomization, which is precisely that idea. And so that's, first of all, even in places where you can implement that, typically those are they're heuristic approaches, right? So in very specialized models, you can show that they reduce bias, but more generally, you can't show that they reduce bias. And so, for example, in this setting, right, if you were to split both the viewer and the streamer populations, right, you would be sort of changing the state of the world, right? Because now, let's say, viewers only have access to half the streamers that they would be interested in, right? And that's a very different world. It's a question, I think it's an open question, how much bias that would necessarily introduce in this setting. But more generally, I think it's very case by case whether you can actually implement that and whether it'll work well.
Thanks.
Thank you for the great talk. I'm curious, how important is the quality of the Q function?
Yeah, that's great. So in the specific setting I showed, it's an episodic RL setting. And so actually what we did in our application is we just used a Monte Carlo estimator for the Q function. So we just sum rewards going forward. And essentially, as long as the Q function is unbiased there, so that's like an unbiased high variance estimate of the Q function. So as long as it's unbiased, as long as you have enough users coming in such that you can average out the variance, then it's great. So that's probably what I would prefer to do, as long as you have enough episodes that you can do this. More generally, if you need to use like a state approximator, a function approximator for your Q function, that introduces further bias, I guess. And there, the quality of the Q function, the quality of the function approximation you're using, that starts to matter a lot.
I see. So if I understand correctly, you're saying that the Q function was really simple in this setting.
So the Q function can be arbitrarily complex, right? The real Q function. Mm-hmm. The Q function estimator that we use is extremely simple.
I see. Okay. Mm-hmm. Thank you.
Okay, so let's thank the speaker again.